Have you ever wondered what a massive bolt of lightning and your tiny phone charger could possibly have in common? Well, it turns out the same basic rules govern them both. Today, we're going to pull back the curtain on the invisible force of electricity. So let's jump right in. I know, it sounds like a strange question, right? One is this huge, chaotic force of nature, and the other is a little device you use every single day. But the answer that connects them, well, it lies in three fundamental properties of electricity that we're about to explore. And here they are, our main characters for today: voltage, currents, and resistance. Now, to really get a handle on them, we're not going to start with a bunch of complex physics. Instead, we're going to use a super simple but really powerful analogy that's going to make it all just click. I want you to imagine water flowing through a set of pipes. That's it. This simple system, pressure, flow, and friction, is going to be our guide to understanding the abstract world of electricity. And believe me, it's an almost perfect one-to-one comparison. All right, first up is voltage. The easiest way to think of it is as electrical pressure. So let's go back to our water analogy. Voltage is like the water pressure building up in a big tank. It's the potential, the push, the force that's just waiting to make things happen. So officially, voltage is the electrical pressure that pushes electrons, and we measure it in volts. The key word here is potential. You know how the pressure inside a sealed water tank is there even before you open the tap? Voltage is just like that. It's potential energy, ready to go, even when nothing is actually moving it. So you've got the pressure, the voltage. What happens when you finally open the tap? You get flow, and that flow is the current. Current is the actual movement, the rate that electrons are traveling through a wire, just like water flowing through a pipe. So the crucial thing about current, which we measure in amps, is that it's all about how many electrons are moving past a certain point every second. And just like water needs a pipe to go somewhere, current can't flow without a complete path, what we call a closed circuit. Now, in the real world, no pipe is perfectly smooth and wide. You might have a narrow section, maybe a pinch in the hose, or just some natural friction. Well, that opposition to the flow of water is exactly what resistance is in an electrical circuit. It's the thing that slows it all down. We measure this opposition in a unit called ohms. Some materials, like copper, have really low resistance. They're great conductors. Others, like plastic or rubber, have extremely high resistance, which makes them excellent insulators because they basically stop the flow completely. And this just sums up the whole idea perfectly. Voltage is the pressure, current is the rate of flow, and resistance is the friction or that pinch in the pipe. If you can keep this mental image in your head, everything that comes next is going to be so much easier to understand. Okay, so we've met our three key players. But how do they all relate to each other? Well, that's where the rule book comes in. A simple, elegant law that governs how they all interact. It's called Ohm's law. This is the heart of it, right here. Ohm's law gives us the fundamental mathematical relationship that connects our trinity. It tells us that these three things aren't independent. They're all locked together in a predictable and kind of beautiful balance. And the best part is how flexible it is. It's one single, powerful equation that you can easily rearrange. If you know any two of the values, you can always find the third. Want to find voltage? Just multiply current and resistance. Need to find current? Just divide voltage by resistance. It's that simple. So, theory is great and all, but let's make this real. Now that we have the concepts and we have the rulebook, it's time to see how they all work together in a simple, practical example. So, here's our problem to solve. Imagine we have a basic circuit, and we want to figure out exactly how much current is flowing through it. First, let's see what we already know. In our example circuit, we know two things for sure. We've got a power source giving us 12 volts of pressure, and we know the circuit has a total of 4 ohms of resistance slowing things down. The only thing we don't know is the current. So how do we solve this? Easy. We go right back to Ohm's law. Since we need to find the current, or I, we'll use the version of the formula that solves for it. Current equals voltage divided by resistance. And there you have it. We take our 12 volts, we divide it by our 4 ohms of resistance, and the result is 3 amps. That is the exact rate of electron flow in our circuit. Simple as that. But you might be asking, why do we even care about voltage and current? Well, because together they produce power. Power, measured in watts, is the whole point. It's the actual work being done, like lighting a bulb or spinning a fan. And calculating it is also incredibly simple. To find the power our little circuit is using, we just have to multiply the pressure by the flow. So that's our 12 volts of voltage multiplied by the 3 amps of current that we just calculated. And the answer is 36 watts. That's the amount of power being consumed. You see how it all connects? The voltage provides the push, the resistance limits the flow, and the resulting current does the actual work, which we measure as power. So what are the big takeaways here? It all comes back to our simple analogy. Voltage is pressure, current is flow, resistance is friction, and Ohm's law is that simple, beautiful rulebook that connects them all together. And that really brings us to the end. You now understand the fundamental rules that govern every single electronic device you own. So the question is, now that you're armed with this knowledge, what do you see differently? What could you maybe build or fix, or simply understand a little better now that you know the rules? Thanks for watching.